Hi everyone. Well, at this point here we've been through 3 gas laws and now we're on to a gas law that combines elements of all 3 into one. So as of this point we've now tackled Boyle's, Charles, and Gay-Lussac's law, each one with their own particular equation. Here's Boyle's, here's Charles, and here's Gay-Lussac's law. So we're going to take elements of all 3 formulas, put them together, and then be able to solve a little bit larger problems. Because instead of having 4 variables, our new scenarios will have 6. So here's what it looks like. We have P1 times V1 divided by T1 equals P2 times V2 over T2. So we have 6 variables, and the problems that we will face will always have 5 variables given to us, and we'll have to solve for the 6th. So it's a little bit more difficult, but still the algebra remains the same in how the problems are done. Just a little bit more movements of the variables when trying to solve for your missing one. Okay, so let's take a look at an example below. It says an unopened cold 2-liter bottle of pop contains 46.0 milliliters of gas, confined to a pressure of 1.30 atm at a temperature of 5 degrees Celsius. There's a lot of information they're throwing at us right off the get-go in the first sentence. So what we can do is we can pause for a minute and we can basically go ahead and start identifying the variables that they give us in terms of what we're going to be putting into our formula to solve this problem. So the first thing that we're faced with is the container's volume, which is 2.00 liters. So that is the initial volume of our container. That's V1. It contains 46.0 milliliters of gas. Now, although that's an extra number, we're not going to use it particularly in this problem because we do have the volume of the container already. The first pressure given to us is 1.30 atm. Atmosphere should be a unit that you're pretty familiar with now, and seeing it you should be thinking pressure as soon as you see it. Temperature is going to be 5 degrees Celsius, so we're going to have our first temperature there, our T1. All right, in the second sentence it says, if the bottle is dropped into a lake and sinks to a depth at which the pressure is 1.52 atm, so that's going to be our second pressure, or our P2, and the temperature is 2 degrees Celsius, so that's going to be our T2. What will be the volume of the gas in the bottle? So in other words, they're asking us what is V2. All right, so as you can see, we have 1, 2, 3, 4, 5 variables, and using algebra we can find the 6th. But before we do that, let's just go real quick and think of a prediction we may have towards this scenario. So we have a 2-liter bottle of pop. Someone throws it in a lake, it sinks down to the bottom. Okay, so we said that as things get colder, as they do in this scenario, as it heads towards the bottom of the lake, volume decreases. So that definitely leads me to think of the volume of the bottle might get smaller. We also know that as things get deeper underwater, pressure increases. So that's another bit of evidence that might lead me to believe that the volume is going to decrease in size as that bottle sinks. So that's going to be my overall prediction, that the volume is going to decrease. All right, so let's take a look at this slide here. And before we go too far, let's just go ahead and take stock of where we're at. We'll design a table of known values here. My P1 from this problem was 1.30 atm. My first volume was 2.00 liters. My first temp was 5 degrees Celsius. And if you remember from previous problems, we said we'll be converting to Kelvin, so we're going to add 273 to that to give us 278 K. Okay. Our P2, our second pressure from the last slide, was 1.52 atm. Our V2 was unknown, so for that I'll just put a question mark. And our T2 was given to us at 2 degrees Celsius, but again, 273 we're going to add to that to change to kelvins, and that will give us 275 K. All right. So we have 5 out of the 6 variables, and what we got to do then is we got to figure out how to get V2 all by itself. So to do that, what I'm going to start with is I'm going to make this screen a little bit smaller for a second so I can manipulate some of these variables. Now we are after V2. We're after this one right there. So what that means is we're going to have to use our algebra skills to get it by itself. Now, when things are on top of a division line, what we learned last year in algebra is we have to divide both sides by them to get it to the other side. So what that means is if we divide P2 from both sides, what's going to happen is it's going to wind up dropping down here and being underneath that division line. To get T2 off of the right-hand side so that V2 is isolated, what we're going to do is we're going to multiply both sides by it. So it would reappear up here on the top with the P1 and the V1. So essentially what's going to happen is this value here is going to come up here and join up with this stuff here on top. So now V2 is all by itself, and our equation that we would have to solve is P1 times V1 times T2 divided by T1 times P2, there's all 5, equals our V2 value. So let's go back to the main screen. Okay, and what I'll do is I'll go ahead and I'll put it right underneath here. Our P1 is 1.30 ATM. Our V1 is 2.00 liters. Our T2, not T1, but T2, you can see it right there, is 275 K. And that's going to be divided by T1, which is 278 K, times P2, which is 1.52 ATM. Okay, all that is going to give me my V2 value. So I've already cranked it through on my calculator, and I wind up getting 1.69. Now, you can double check it to make sure you're getting the same thing. But the next question is, okay, so there's a lot going on here. What unit do I put? Well, as long as you put your units into the problem, it's going to be no problem at all to figure it out, and here's why. When you have a unit over another unit with a division line in between, they cancel out. So my ATMs go away. My L's, I see one here, but I don't see anything on the bottom, so I got to leave it. But I do see a K here, a Kelvin, and a Kelvin underneath the division line. Those divide out. So what we're left with then is just the one non-crossed out unit of liter, and that's going to be the unit we're going to add to our answer. So we have 1.69 liters as a final answer. Okay, I chiseled it down to 3 significant digits because, as you can see here, most everything in this problem is 3 significant digits. So my answer follows suit. 1.69 liters equals my second volume. Does it match our prediction? Absolutely. We started out with a 2-liter bottle. We said due to the pressure of going underwater and due to the colder temperatures down below, both of those things would lead to a smaller volume, and indeed it did. 1.69 is smaller than 2. So I hope you understand the combined gas law a little bit better now. Again, it's just elements of Boyle's, Charles, and Gay-Lussac's laws all combined into one formula, and we'll be solving for the 6th variable if we're given 5 of them. So good luck with these topics. I hope this helped. Study hard, and I'll see you next time.